Okay, so we're continuing our look at some properties of definite integrals. I'm actually going to give you two definitions right now. And these are in your book, but they don't have a number associated with them. If I take the integral from a to a of f of x dx, now that looks a little bit weird because this number and this number are exactly the same. A little bit of vocabulary here, might as well throw this in. This is called the lower limit of integration. And this is called the upper limit of integration. So they're the endpoints of the interval over which I'm integrating integration. Okay, and we call those things the limits of integration. Now, just like with limits of summation, which was my starting index and my ending index, I think it probably makes the most sense at this point to just think of this as we're using the word limit in two different contexts. There is a connection to these being the limits of integration and limits as we know and love them, and those of you who take 3B will actually explore that a little bit next semester. But for our purposes right now, these are just the endpoints of my interval. They're called the limits of integration. I'm going to just think of that as using the word limit in a new context. Okay, so here I've got that the limits of integration are the same. So if I think about what's going on here, I've got some function f of x, I've got some x value a, and I'm really looking at something like so. This would give me what I call a degenerate rectangle because the base would be 0. The length of this interval is 0 because its starting and its ending point are exactly the same. So if I'm thinking of this as the signed area between the curve and the x-axis, that really ought to be 0 because it's a degenerate rectangle. I don't care how big the height is. If I multiply it by a base of 0, that's taking up 0 two-dimensional space. Okay. So that is a definition. If my limits of integration are the same, we say the integral is 0. Now you might sort of say, okay, that makes sense, but do we really care? Okay, why do we need to know this? Am I ever going to want to calculate an integral like this? There are actually two good reasons for having this defined. One we will see in the next section. We're going to be defining an area function that's associated with f of x. I'm thinking of this as a height function. We're going to be able to create a new function called an area function. And when we do that, this definition is going to be important. The other reason is that in section 5.5, we're going to learn a technique of integration called U substitution. And one of the things that sometimes happens in a U substitution is maybe you start out integrating from 3 to 4. Okay. But when you do this technique, the limits of integration change. And sometimes they change so that they're actually the same. And now we've defined what that means. Okay. So it does seem kind of wonky just out of the blue. Why would I ever do this? There are some good reasons, and we will be seeing them in the coming sections. Okay. Next definition, and this is also a definition, is the integral from b to a of f of x dx is the opposite of the integral from a to b of f of x dx. So up until now, we've always been integrating from left to right. So if I was integrating from a to b, it was kind of understood that a was the left endpoint and b was the right endpoint. And that way we were always saying the base was positive, and so it was the sign of the height that would determine whether we were getting positive or negative signed area. Now, I've drawn this picture so that A is the left endpoint and B is the right endpoint. So over here, this would be integrating backwards. This would be going from right to left. When we do that, what we do is we essentially now count the base as negative because now we're going backwards in the negative direction. So if I were integrating from B to A, I would count this as having a negative base and a positive height, so I would get a negative area. And it would be exactly the opposite of the area I would get if I integrated from left to right, the way we're used to doing it. Once again, just like with integrating from A to A, it might seem like, why would I ever want to do this? Okay, so just having the definition, it's not clear why we need this. Same two reasons as why we need the integral from A to A. We are going to be defining this new function called an area function in the next section, and this is going to make that definition apply for the entire domain of the height function. And then in section 5.5, we're going to learn this nifty technique called U substitution, and sometimes that does change the limits of integration. And so you might have started out with a perfectly nice problem where you were integrating from left to right. You apply this technique and your limits of integration change, and suddenly your lower limit of integration is to the right of your upper limit of integration. And that's okay. We've defined what's meant by that. Okay. So a few more properties, and the rest of these do have numbers. So this is property number 1 in your book. It says if I'm integrating from A to B, C dx, where C is just a constant. Well, let's draw a picture. So let's say I'm going from A to B. My height function is constant at C. Now I've drawn C as a positive number. Could just as easily have drawn it as a negative number or even 0. Okay. But I know what this represents. This is going to be signed area that I have right here. But if that's a constant height function, then I'm just going to get that height times the length of my base. I'm getting the signed area of a rectangle. And of course, if C was negative, this would give me a negative signed area. Okay. So kind of nice. We are going to learn some techniques for integration. Usually when I see something like that, I evaluate that by just thinking of it geometrically. I say, oh, constant height, I'm going to get that height times the length of my base. And for those of you who go all the way to 3C, this concept of thinking geometrically about what it means when you integrate a constant, you're going to see that more and more in 3C, but in higher dimensions. Okay. So kind of neat to have that geometric interpretation of the integral there. Okay, property number 5. Remember, 2, 3, and 4 were the ones that we did in the last video. Okay, so I'm just not covering things in the same order. Okay, this says the integral from A to C of f of x dx. Did I do A to C first? Sorry. Yes, plus, here we go, plus the integral from C to B of f of x dx is equal to the integral from A to B of f of x dx. Now, I'm going to draw a couple of pictures here. The simplest situation is if A is here, C is here, and B is here. So I'm not going in alphabetical order, but essentially here we're saying I'm going to integrate from A to C, and then here I'm going to integrate from C to B. And if I put those pieces together, I'm integrating from A to B. So if here's my function f of x, I can see the integral from A to C would represent this signed area. The integral from C to B would represent this signed area. And if I add those together, I'm just getting the signed area over the interval from A to B. Okay? So that picture makes an awful lot of sense. But now, there was nothing here that said A, C, and B had to be in this order. So what if I did put them in alphabetical order? What if I had B here and C here? So now, the integral from A to C would represent all of this signed area counted as positive, because I'm integrating from left to right and my height is positive. The integral from C to B Well, that would be this area, but from B to C, now I would be counting that as negative because I'm going backwards. I'm going from right to left. Okay. And they're saying that's equal to the integral from A to B. Well, yeah. This whole area minus this area just gives me the left half. So this property is true regardless of the order in which you put A, B, and C. And it's kind of fun to just play around with ordering A, B, and C in different ways and just drawing the picture and say, hey, yeah, that works in that order too. So I could put C over here, I could make B first. You can draw a picture to illustrate this for any order that you can put A, B, and C in, and property 5 says that this is always true. All right, we've got just one more video with a few more properties, and then we're ready to move to the next section.